So let's have a look at the example problem now in ABAQUS. So we'll follow all the different steps as I described before in Getting Familiar video. So I still have the same window open, and what I want to do now is I'm going to change this model name to one element, because this is the one I'm going to only create one element for the entire bar. So I have to create a part, and that's quite simple. It's just going to be a 1D part. So I'm going to use 2D planar in this case because I don't want it to move in the third direction, which is in the out of plane direction. So I just say, okay, it's 2D planar. So I have an XY plane. I want a deformable body because I want it to move. I'm going to use a wire because it's just going to be a bar, so it can be idealized as a one-dimensional element. And since the length of the bar is more than 200, I can safely use it as a 400 approximate size grid. And this is just the drawing space size, which is going to just show up when I click on continue. Before that, I can change the name of the part into a bar. I say continue, and this is the grid. So if you see, these are like 10, so then you have 20 in this direction, 20 in the other direction, so you can easily form your part. This one is quite easy. I just want to make a certain length. Now what you see here is a number of options. If you have worked with CATIA, this may look very familiar. It's kind of similar GUI. So these are all the different options you can use or tools you can use to create your sketches, which can be then later extruded or made into planar or revolved, etc., depending on the part you want to make. It's also possible to make a part in CATIA or any other CAD program, and then import it. Sometimes that is easier if you have more complicated parts, because the drawing options here are not extremely good. However, they are better than some of the other finite element programs available. So in this case, I just want to make this bar. So it's just going to look like this. The only thing is I can give it a dimension to make sure that it is 250 in length. So that's the only thing I want to do. Here you can see that there are different options that keep showing up here, and you can click on certain things. If you want to go back, you click here. If you want to cancel the process, you click here. And if you're done with your sketch, you can click on done. You'll also see that I see different kinds of toolbars here on top when I'm inside the sketch. With this option, I can do the magnifying. So with this, I want to fit it in. I fitted it into the screen, so I see the whole length of 250. I'm done with the sketch. So I'm going to get out now, and this is what the sketch looks like outside of the grid. It's still 2D planar, however, it's lying in this 3D space in the XYZ, so I can still move it around. So you can see here is the axis, and these are certain grids that you can use for inbuilt axes that you can see, like views. So this is aligned in the X direction, which is easy for us because our problem was also aligned in the X direction. However, if you made it vertical, then you just have to be careful that it's aligned along the Y direction. So these are some things that you will practice, you will get used to it, and then you'll be able to manage things in different coordinate systems later on. So now, since my part is created, I want to put in all kinds of information into it. So first, let's start with a material. So I want to put in a material, and if you can look carefully, it clearly looks like properties of aluminum. So I'm going to do add properties of this material. You will see that there are many different things you can do. First, you can add a description here. So you can click on this pencil and you can say simple properties, or whatever you want to add. You can add a certain text so that you remember. If you have a lot of materials, then you can add a better description which makes more sense. This is important when you see the text file, which is generated as the input file later on. So you can find all this information written down like comments in your code. If you look at density, you will be able to put within this material density, regularization, and the mechanical. You have 100 million options here. So if you want to find out about everything, you can easily click on this help button, click somewhere. But in general, you will be using a lot of this one, mechanical elasticity. You will have to provide a density if you are interested in the inertial properties, but right now we don't need those, as in inertia, as in the sense of gravity, not the moment of inertia. And with mechanical properties, we will be doing elastic mostly because we are always in the linear domain, and it gives you different kinds of options. You can have isotropic, you can have different kinds of properties here, like engineering constants. If you know the properties in different directions are different and you have all the values with you, you can choose all different kinds of options here. So if I go to engineering constants, I can put in a lot more than just one. For example, for composite materials, this is very commonly used one if you have a 3D model. However, we'll come back to isotropic because that's what our material is defined to be. The Young's modulus and Poisson ratio is given to us in the problem. We're going to enter those and we will just do OK, and it will create a certain material. So you can keep uncollapsing this to see what's happening. So you have a new part which is called bar, and under the part we have many options. We are going to go through them later. Then you can have material. You can define a lot of materials here. Now once you have defined the material has to be applied to this bar, but you can't do that directly. So first what you need to do is you need to create a section. Now this is just a bar element, it's a truss, so it doesn't have any particular cross section. But if you did have a cross section like in a beam, then you could create a certain cross section by means of using profile. And here you see you have a lot of different profiles that are available to you. The shapes of a box, pipe, circular, I section, L section, T section. You can also create your own section which is arbitrary. So this is an option that is available to you. We will use it, but not for this problem. So we can just skip directly to sections. Under section, if we say I want to create a section, which is basically a truss, and it's a beam because it's 1D, and under beam you will see you have two kinds, beam and truss, and in this case we want truss because that's the one which has the degrees of freedom only in the axial direction. So if you press continue, you get the option of what material you want to add. If you had more than one material, it would give you a choice, but now you have only one, so it automatically fills it in. And here you can give a cross-sectional area. Now, I just used the same equation to check the cross-sectional area, but you can also find out the cross-sectional area as an average. So what would be the average between the front and the last section to give you sort of a rectangular section in between. And the value is 117.8.18. So that's the value of the cross-sectional area. We put that in. So we have a section which has been defined. We have a section which has a cross-sectional area and a material property. So if you think carefully, for the behavior of the element, we had K is equal to EA by L. We already have E in terms of material. We have given the cross-sectional area and we already know the length because of the geometric condition of the part. Now we can just apply it to this bar. So we go to section assignments under the part. So under part you have bar, and under that you have section assignment, and we want to assign this section to the entire part. Now it'll keep giving you an option to create a set. You can leave it on if you want to create a set, but I would like to create my own sets so I know which set corresponds to what, instead of just set 1, 2, 3 and I have to keep clicking to find out what exactly it meant. So you can also unclick this if you would not like to use this option. And I say, okay, I want to create a section. I want to assign a section. So I choose this part just by dragging and picking up. And I do done. It's going to ask me, do you want to apply section truss? And I say, yes, I would like to, and do OK. So this section has been assigned to this part. You see the color has changed from whatever it was to, I think, white to green, which means the sectional property has been assigned to it. Now this is a really simple problem, so we don't have to think about orientations, we don't have to worry about where it's lying in space, etc. It's just going to go in one direction. So it's quite easy. However, we need to do something more. We cannot assume that the finite element program will automatically create a mesh on it. So we need to create elements, and creating elements is called meshing. So if you come to this section which is called meshing, we can also use, let's use this one just for fun, to get you acquainted to it. So if you look at the module and you go to mesh, you will see that you can add a certain properties here. So if first of all, I want to make sure that the element type is correct. That means the behavior of the element is exactly what I want. Strangely enough, it's not letting me Okay, I'm in assembly section, that's why I couldn't see it. So if you click on part, it shows you the part in pink, which means there's no mesh on it. And I'm in mesh module. So here, if I click on this one, it's going to help me assign an element type. Now, luckily enough, we've checked this and it's not correct because the standard element library it has picked up in the linear geometric order is a beam. But our element is not a beam, it's a truss. So we need to go all the way down, pick truss. And there are some options that keep coming up here. This is not really important for us, so we can leave this. And you see this is the name of the element in ABAQUS, T2D2, which means it's a 2-node linear 2D truss, which lies in XY plane. If you do OK, that means the element that will be applied to this part is going to be a truss. Now we can choose how many elements we want on it. So you can seed the part by doing this, or you can also seed the part by doing this, by using edge. It's just one edge, it doesn't matter. So I can also choose what is the approximate global size, and I know the size is 250. Or I could choose the other option, which is this one, which says I want to use an edge to seed. And I would say, then it asks you to pick up. So I'm going to pick this one. And once I go into it, I can either choose what is the size or I can choose a number. And here I can easily give the number 1. And you see these pink boxes show that there's only one element. And if I mesh it, I will get nodes at these 2 edges. This is not meshing, this is just seeding it. So we've decided where to put the mesh. Now, if you want to put the mesh, you have to click on this one, which says mesh part. And once you click that, it says, do you want to mesh the part? And you say, okay. And here in the message window, you will see one element has been generated on part. Okay, the English isn't very good, but we can forgive that. So one element has been generated on our bar. Now if you think carefully, most of the steps, so discretization, element behavior, meshing it, so we have everything has been done. Now what we need to do is we need to set up the boundary conditions and the loads. Before that, we have to create an assembly. I know it's just one part, but that's just how ABAQUS works. Even if it's just one single part, you have to import it as an instance into assembly, and only on the assembly you can apply boundary conditions, loads, etc. So if you just pick up instances and you say, okay, yeah, I want to pick up a bar, you do okay. But also to tell you, you can pick up bar multiple times so that you can have many bars put together into a larger structure. But we're not going to do that because that's not what the problem requires. So we have an instance, which is bar 1. It's always written as this. Bar 1 is the instance for the part bar. So you have an instance now, and I want to create the loads and boundary conditions. So if you remember carefully, I first have to create a step. I'm just going to call this step axial load because that's what's being applied in this step. I can give a description that there's a load P acting on it, whatever text I want to write, and everything else remains as it is. You don't need to change anything. This is mostly to do with what kind of solver you want to use when you have a non-linear analysis, and we don't have a non-linear analysis, so we don't have to worry about this. Now our step is created, and you will see that as soon as you created this step, you have this F output 1 and H output 1 created for you. It wasn't there before. So this is a field output, which is basically means all the outputs that are happening in every step of the analysis will be saved here one by one for all different things you ask for. And the history output is going to give you the output throughout the analysis. In linear analysis, it's very rare that you would have different results, but in the history output, you can make nice charts for the entire duration of the analysis. That's the only difference here in this case. In the nonlinear analysis, it means much more, but we'll keep that for the next course. So you can change things here, but we look at it at the end. So now after creating this step, we can now put in the boundary conditions and the load. So I'll go to boundary conditions. Now in boundary conditions, you would see that you have certain options given to you when the step is axial load. And when I select initial, some other boundary conditions will show up. So be sure you know what kind of boundary conditions show up, so you know when to use which step. Now the boundary condition can be used in the initial step because it's just going to be fixing it. I'm not going to apply any load. So let's say I call it fixed, and I want to use symmetry, anti-symmetry, and caster. And caster basically means fixing it. And I continue. I will select the region here, and I will fix it completely. So I'm going to say encaster. I want to fix all the degrees of freedom that are possible. Although for this element, it's not active, but I'm just going to do it anyway. Then I will create a load. In this, you see, if I have a load I cannot put it in initial step. So I have to switch to step action load. And I'm going to name this load P because it's called P and it was a concentrated force, and you have many other options. Like you can see, we'll choose some of them later for other analysis. You press continue. You will select this point here on the right, but this is where the load is applied. And you will put in the value of 1 kilonewton. And that's where the load is set up. So you can see it very clearly. There's an arrow pointing to the right, which is the load. So you have your boundary condition and your load, everything set up. Now let's come back to the field output request. What do I want as output? It shows me a lot of things. I don't want everything, so I'm just going to unclick everything. You see, as I click, all these things disappear. What I would like to see very much are translations and rotations, although there are no rotations. I would also like to see what is the strain, and I would also like to see what are the stresses. Maybe the one Mises stresses are good. You can also choose particular kinds of stresses. So you want transverse shear, etc. Although they don't exist in this model, there are possibilities to see it in other models. So we have strains, we have stresses, and we have displacements. And I don't want to see anything else. Well, I could also see something interesting here. Like, let's have a look at reaction forces. So I just want to see the reaction forces because then I can do a verification of whether my model is really in equilibrium at the end of the analysis. And I say, okay. Within the history output, you don't have to choose much. You can also just say, I don't want to see anything. And that is not going to help you because it says you have to choose something. So let's just leave the energy on. It doesn't matter. We don't have to have a look at it if you don't want to. So now we've set up the problem. Let's just recap. We made a part. We created a sketch for it. We came back. We created material. Using the material, we created a section. We put the section back in the part. Then we chose the element type we want to use. We put a seed of how many elements we want to put, and then we actually created the elements by using the mesh option. Then we went ahead and imported this part into assembly as an instance. We created a new step so that we could apply a load. So that was an actual load step. And then we put the boundary condition and the load. And we also chose some output that we wanted to see. So once all that was done, we can now go directly to creating so the pre-processing step is now over. So we can create a new job. I'm going to call this job 1 element, and it's going to be part of this model, which is already created, which can be chosen, which is already here. You can see 1 element is the model, and then you can do okay. You don't have to change anything here. It's not required at this stage, but you can always click on things and see what it means, but we don't need to use it. If I'm going to click on everything and try to teach you everything, it's going to take a year. So I would say just practice a little bit and, take your time, get used to the software. But all the most important things I will point out to you. And we will do many more tutorials, so there's nothing to worry about really. Once you've created this job, I'm just going to do right click and then run it. So I'm going to say submit. It's going to do all kinds of preliminary checks. If I've made any mistakes, this is the point where it's going to tell me that I forgot to put in values, or I forgot to mesh it, or there are missing properties. And then I can go back and I can check what went wrong. So when the analysis is running, I can right click and I can say, okay, I want to monitor what's going on. So if you look here, I have some things going on. You can see that there are some steps. There's 1 step, 1 increment. And while I'm doing this, already the analysis is completed. But I do see some warnings. And the warning is that the request for Mises output will be replaced by a request for S output. So the only thing I'm seeing is that output wasn't the correct one I should have asked for, but it's just replaced by another stress output, which ABAQUS thinks is relevant. And that it can do for you for many options. So if there's a warning, it's not a critical thing. But if you do see an error, then it's a serious problem. And then you need to go into your message file to find what the error is. And that can give you a certain idea of what's going on. If you also look into your message file, of course, I want to make it bigger. You can see how much time it took for the analysis, how many increments it carried out, etc. It's just linear, so mostly it's always going to be 1. You can always change that, but it's just going to make more points, but it will be a linear result. So it took about 0.1 second and a CPU time of 0.2 seconds to complete the analysis. So it's completed. I can have a look at the results. So I do right click and I go to results. And it automatically switches to another section which is called results here right next to the model. And here I'm seeing a condition which is undeformed shape has been plotted. I can also plot the deformed shape without any color. So what's happened, if you look carefully, it extended. Now I also want to see it extended with some colors on it. So I can see how it extended. Now when I pick this, it just shows one color because of course there's only one element. So we have only one result for the stress throughout the member. But what I'm really interested is in the displacement. And here I can choose U1. Now if you see U2 is going to be 0 because it's a truss element and that's verified. Now you can increase the size of this these numbers here. You go to viewport annotation options, legend, set font, and then you can increase the size up. The downside is that if you do this, you have to do it every time. But there's a permanent fix, and I will put it on Blackboard so you can actually put that into your problem. Then it's much easier. So you can see that the U1 is varying throughout the length. So it has extrapolated, but first it calculates at the two nodes, and then it extrapolates the value because it's just linear. Now we know that here it's 0 because we forced it to be 0. So you see it's 0 at the left edge, and at the right edge you have a maximum displacement of 3.048 10 to the power minus 2. So you should make a note of it, or you should save this result somewhere so you can compare it with the next model. Let's use the query sign. The query, let's pick a node. Now I want to see what is the displacement at this node, and it'll show me the exact value. Now there are no other nodes here, so I can't pick anything. The only other node here is this one, which has 0. So it shows me that the magnitude of displacement is 1 e to the power minus 33, which is practically 0. So that was the setup and the results for the model with one element. I hope that was interesting enough because we're going to do the same exercise now for 4 elements in a different video.